Yes, the research say he's optimist, and also, you know, when you
no, I'm an optimist.
most of us, if you read that, I mean, it's like conservation, remote sensing. I mean, he's just like, you know, a Renaissance person. So.
Well, Pat, that's very kind, and thank you for the invitation to come to USF, and it's been a fabulous day. I haven't stopped talking, so I hope I don't go hoarse on you midway through. So I'll be talking about, well, several things, but emergent behaviour will be a central theme to the presentation in carbon on ecology, but also which is here. This is the skyline of Miami behind, so right next, very similar. This is the University of Miami Underwater Studies class going on over here somewhere. And I joined University of Miami relatively recently. Going there was, of course, a great department. There's been a lot of interactions between people here in the audience and the University of Miami, and in particular, this is, of course, Professor Ginsberg, Bob Ginsberg, and I mention him because he left a very actually to our at the moment. So if you or anyone you know are the next Bob from positions, there'll be a senior position in chair and a junior position. So in terms of my presentation, I will take you first of all on a grand tour of modern carbonates, which is work I've done with the Living Oceans Foundation over the last 10 years or so. I'll then talk about emergent behaviour in carbonate depositional team here at the university. I've got several PhD students and postdocs, and with a project with the Living Oceans Foundation, which have this fabulous vessel. It's an 86-meter vessel, and it has an aeroplane on the back. It's very James Bond. And this is a big, powerful elevator, and you can lower the aircraft into the water, and then you can start to fly surveys in areas that you couldn't ordinarily. Just retired from the Navy. He said it has to be something to do with living oceans. Phil, I work on coral reefs, and there's many areas in the remotest reaches of the oceans where we really don't understand how the reefs are functioning, and this would be a great way to put in a global baseline. We could take your ship all the way around the world. It was a lie. I mean, what I really meant is if I had such a ship, I would take a long holiday, obviously, but I didn't say that. And he said, and then he tucked into his meal. And then a few weeks later, Phil called me up. I'd given him my card, and he said, "Oh, Sam, why don't you tell me more information about this idea you have with the global reef expedition using the ship?" And I couldn't believe it at the time, but we ended up actually doing it. So we started in 2006 in the Red Sea, and we finished in 2016. So it was a 10 years at sea. We had the ship for about 4 to 5 months a year. And now we're deep in the lab work. and we visited 15 countries and 1,000 reef sites. More than 200 scientists were involved, not all on the ship at the same time. It'd been a bit too cozy, but over the different missions that we did. And they logged more than 15,000 hours underwater, and everyone came back alive, so that was success. And we made more than 65,000 square kilometers of meter resolution seafloor maps, bathymetry and habitat, which is about 1/5 of the world's reef, something in that order. And this was the route. We started in the Red Sea here, where we did 3 expeditions, sort of shaking down our protocols. And then we came across to the Caribbean, based the ship in Miami for 18 months, and then down through the Galapagos and French Polynesia, all the archipelagos of French Polynesia, and then the Cook Islands and Tonga. And then we popped out over here in Fiji and New Caledonia and up to the Solomon Islands and through the Coral Triangle and the Great Barrier Reef, and then out to the Central Indian Ocean, to the Chagos and the Maldives, and then back to the Red Sea. So that was a 10-year mission, and we just recently published the maps, actually, that we produced. And we did a lot of work. We looked at a sort of holistic. We looked at the biology, and we had experts on fish and corals and the diseases they suffer from. We did oceanography and chemistry, looking at acidification questions, and also geology. We collected a lot of low-fold seismic and sub-bottom and sediment samples and cores and so on. And what you realize is when you start swimming around on the reefs, like my colleague is here, that, I mean, it's a very good way of collecting data, but it's really a drastically offset from the scale of the entire depositional environment, which sprawls over hundreds of square kilometers, often thousands. And really, when you talk about reef degradation, which is going on at a really frightening rate, you're really from the scale of the problem, which is really sort of global in nature. So with that, we carried on, and we did a lot of in-water work, but we started to concentrate more on the remote sensing platforms that we could deploy. And of course, we had this fabulous aircraft on the back of the ship, and so we started to use it to its full potential. So here it is. It lands on the ground as well. It's got little wheels that come out. And before we could start to really do aircraft to fit the sensor packages, which involve like cutting various holes in the fuselage. And there's 2 groups of people that become very excited when you start to modify the aeroplane. The first is the Federal Aviation Authority. They become very excited, and we got through that. And then the second hurdle is the owner of the aeroplane. They're not always particularly keen on you cutting holes in it, but we got through that, and we mounted a sensor package here between the floats, and to do remote sensing. And this was using hyperspectral surveys, and we did some laser altimetry as well. And when I was doing my PhD, I'd worked on these sort of problems of how to resolve bottom reflectance and to get some degree of optical closure when you're overflying with a satellite or an aircraft. So we had some basic workflows that we could start to scale up. And the products, we convolved satellite and aircraft imagery depending on where we were working. So this is an example from the Solomon Islands, and you have these beautiful images. You can see the reef nicely resolved here and then out into the deep and dark water. From that, we could also resolve the seafloor topography down to about 30 meters water depth, either using LiDAR altimetry or spectral derivation of water depth. So we have the images, and we have the bathymetric maps, and then we started to produce habitat maps, which there was a lot of emphasis on this work into very vigorous ground truthing, rigorous and vigorous ground truthing. So we really have a high degree of confidence that when we classify an area of being a particular seafloor type, it's correct. And so then we have these maps that we produce and then start to scale them up gradually and globally. And we took all of those data and we produced these atlases. So these are expensive to print, large format books. You know, it seems very archaic really, but what we found is that many of the nations we were visiting, they responded very well to hard copy books. And with this, the preamble would say about the sort of benthic habitats which exist. This is one for the Red Sea and another one for the Bahamas. and then we would lay out the maps, the bathymetry and the habitats, in the hope that we would kickstart meaningful conservation initiatives in these countries. And in some cases that was very successful, like in Solomon and Tonga and the Bahamas actually. In other cases we weren't quite so successful, but if the host nations who invited us to do this work, come round and they want to start looking at marine conservation, we stand ready to help them with that process. And of course we take all of that data, we don't just put it in books, we also have a map portal on the website, and you can see this is a bathymetry map, so you get these little camera icons and you click on them, and we have hundreds of thousands of seafloor videos which show what the seafloor looks like. So really we had a great data set, 65,000 square kilometers, about a fifth of the world's coral reefs mapped to meter resolution, and then you can start to do science. And one thing which I became very interested in was this concept of emergent behavior, and we really had the really big data sets that you could start to look at this systematically. So emergent behavior is a hallmark of complex systems, and it presents itself often as coherent patterning, as you can see on the front of this book. This is work I did with Dave Budd and Liz Hijek, which is sort of a primer on self-organization in carbonate systems. And we start to see this coherent patterning appearing because of interactions between the organisms in the environment and the organisms with the environment. And you get certain tipping points, and then you get this incredible, in this case for coral reefs, this reticulated sort of patterning that you see in the platform interior of reefs. And we try to understand what's going on here. And I give some examples. This is a nice satellite image from Pearl and Hamies Atoll of the northwest Hawaiian Islands, and you see the reef ring here. And this very interesting thing starting to happen in the lagoon, where you've got reefal reef meters up until kilometers. There's another example here. We're now offshore the United And if you look at a smaller shoal here, which I zoom in on with the satellite, you see this very dense honeycomb organized patterning on scales of really just a few tens of meters. And if you go there and you break open one of these ridges, you see that it's a coral algal matrix. It seems to have been built by the reef architects themselves, and something's going on persuading the architect to form this sort of patterning. And we started to question why, what is going on here? And then you could have several hypotheses, which might be abiotic in nature or biotic. And if you're a carbonate geologist, I know many in the audience are, you immediately start to think about karst, because karst is the subaerial erosion of limestone by rainwater and weathering once it's exposed. And if you work on modern reefs, you understand that in the last 125,000 years, they've been exposed high and dry for at least 100,000 years. So there's plenty of opportunity for karstic type erosion. And this is an aerial photograph from the Darai Hills of Papua New Guinea, 1 kilometer scale bar here. And this is a limestone terrace which has been eroded subaerially. And you see you get actually a very similar honeycomb patterning with lows and highs. And you might well imagine that if you have this going on through the Pleistocene and then you flood these modern reef systems during the Holocene transgression, that the corals will be persuaded to occupy the ridges, and they won't be so keen on occupying the depressions, which will be sediment filled. And when you see this sort of patterning in a modern reef system, you're just looking at a veneer of coral which is accentuating an underlying template which has nothing to do with the biology of the system. Well, I used to think that was the case, but I'm quite convinced that it's not the case now, and biotic self-organization has much to say about this. And this realization came when we were starting to work out through French Polynesia. So this is the Gambier Islands and the Austral Islands, and you could go to any one of these atolls, and I'll take Mantavia here as an example. There's a satellite image, and you can see in the platform interior you have this beautiful reticular patterning. And so is this the accentuation of an underlying erosional surface, or is it something very special about the biology? Well, we know a lot about the subsurface of these atolls in French Polynesia. There's been a lot of coring and seismic done, primarily because there's minimal phosphorite deposits on the lagoon floor. These were formed during marine isotope stage 5e, so 125,000 years ago, where you had dense cyanobacterial stromatolitic facies in the lagoon, and through phosphogenesis they laid down these phosphorite deposits. And what the seismic and coring shows that yes, the underlying Pleistocene surface is irregular. I mean, it's been exposed for 100,000 years, but the phosphorite which was laid down takes away that topography and leaves you really with a flat, featureless surface. And then you have the Holocene transgression, which comes in and floods the lagoon here, and any Holocene reef building which is going on is coming from that flat surface, which indicates that you're not accentuating some underlying template, but this is something to do with the biology of the system which delivers this emergent patterning. And we started to look at a global data set now. So this is a map of the 430 odd atolls on Earth, and we visited each one with satellite imagery and ground truth in many cases, and then ranked them according to how the platform interior reefs have organized themselves. From simple patch reefs would be a rank 1 up to this beautiful reticular emergent patterning at the higher ranks. And you can see that about 30% of atolls globally have some degree of what we would call emergent patterning, and there seems to be spatial clustering as well. You have a hotspot out here in the Coral Triangle, and also in the Indian Ocean, and out here in the Southwest Pacific. We don't quite understand the clustering yet, but certainly this isn't something which is not rare. It's quite consistent. And well, Gene would know, if you presented something like this to Bob Ginsberg, he would say, so what? Like, why on earth should I care about this as an ecologist or a geologist? Well, as a geologist, I think there's 5 reasons why you should be concerned about self-organization in the rock record. And the first is that this imparts what we call autogenic control on the stratigraphic anatomy of the deposit which is laid down. So these are processes which are internal to the system, to do, as I say, with the organisms and the environment that they create through their interactions, and can be quite decoupled from the typical allogenic forcings of the system, which would be widespread changes in sea level or climate. This is something internal to the system, and it yields very complex stratigraphy. I mean, that's I'm talking as a geologist, but I think you could say it's a very complex ecology as well. So as a geologist, carbonate geologist, in the best case scenario, you lay down facies, we call them, sediments with distinct character, which are well delimited by water depth. And therefore, if you look in the rock record and you see a stack of these environments, you can reconstruct the presence of the position of sea level and look for cycles and all the things that geologists enjoy identifying. Unfortunately, when you have these emergent patterning, you get a much more complex stratigraphy because the facies, the sediments, are not well delimited by water depth anymore, and it becomes very difficult to then start to read the rock record to reconstruct what was going on. This is also, from an ecological point of view, much more complex than the sort of textbook model that you would hope for. And this obscures cyclicity and makes for a very complicated system, but I'm going to show you it actually gives surprising mathematical predictability as well, which is a hallmark of self-organization, and through what we call tipping points, it can also have drastic ecological consequences. So I want to first talk about that mathematical predictability, and I have to show a graph here which I'll explain as well as I can, because I've been coming back to this plot several times. So these are the sort of data that you could harvest from a map of a carbonate depositional system, a coral reef map, and I'm simply plotting here, and these are just synthetic data, the probability of encountering a geobody, a particular depositional unit, versus the size of that unit. So this is probability, and both axes are on a log scale. So that's a 100% likelihood of encountering an object equal to or greater than the size on the x-axis here. 10% probability, 1% probability, and the size here is also log 10, 100,000. Let's call them square meters, but it really doesn't matter for the time being. And there's three distributions here which are really important to understand. Now, the first is the red line, and this is what we call a fractal distribution or a power law, which simply tells us that you've got an exponential decrease in the likelihood of encountering a given object coupled to an exponential increase in its size. And you can see that the relationship between size and frequency doesn't change throughout the distribution, it's just the slope of the line. Then the blue line here is what we call a negative exponential. It's very similar to a power law, but it says that we have an exponential decrease in the likelihood of encountering an object coupled to a linear increase in its size. And the green is a sort of interim. We call this a log normal distribution, sort of halfway between a power law and an exponent, which I don't need to go into. I mean, they're very sort of similar in their distribution. So why do I tell you about this? Well, some years ago when I was doing my PhD, I was working with Wolfgang Schlager, and I think many of you have met and worked with him in the past. And at that time, this was in the early 2000s, Wolfgang, he'd bought a book on fractals. And he was pacing the corridors with it, and he was expounding the virtues. And of course, I didn't understand what he was talking about. I pretended I did. And I started to work with him, and gradually I understood it, actually. And we did a little study, well, quite a big study, actually, in the central Indian Ocean. And we mapped out all of the reefs on the Chagres-Laccadives Ridge, which runs down here through the Indian Ocean. Really large areas. That's the Maldives, this is the Chagos down south. And we mapped all the reefs and their sizes from scales of 1,000 square meters, which is just a sort of few increments of this room, so little patch reefs and lagoons, up until entire archipelagos at tens of thousands of square kilometers. And then we started to plot the reefs on this familiar axis of the log probability of encountering a reef versus its size, and you see this incredible linear relationship, which shows that the frequency of the reefs is predictable by their size from less than 1 square kilometers up until nearly 40,000 square kilometers. So that's 1, 2, 3, 4, 5, nearly 6 orders of magnitude. And over that range in scale, the relationship's really simple, actually, that reefs that are 1 order of magnitude larger tend to be 10 times less abundant in the system. And it's like, why on earth would Mother Nature be speaking in this, very consistent language? What's going on here? And being a carbonate sedimentologist, we don't look at reefs only. So this is work in the Bahamas, where we start to map out the ooid grainstone deposits in the Bahamas. This is the tongue of the ocean deposit and the exhumas and the schooners. And we plot the size of the individual sand shoals versus their probability. We don't have a power law here, a linear relationship, but we have lovely exponentials. That is, you have a exponential decrease in the likelihood of encountering a given shoal coupled to a linear increase in its size. Very highly predictable. And that becomes really interesting when you start to look in the rock record. So this is an example here. This is just a seismic horizon. I could have taken any from a carbonate system. This is Aptian in age, so Cretaceous, from the Arabian Gulf, work by Lyndon Jose and Christian Strohmeger and colleagues. And in the seismic horizon, they've imaged a lagoonal system here, and we're working out across the platform margin. And you have patch reefs here growing in the lagoon, in Cretaceous in age. And of course, we're in the Cretaceous, so these aren't coral-built patch reefs, these are rudist bivalves. And you can very nicely start to digitize at least the larger units here. Now, if you believe that such a system follows this predictability, it might well be that you can take seismic data, which is a fantastic technology, but rather scale limited. There's a finite resolution you can get from seismic, and you could start to digitize all of the patch reefs here in the lagoon, and then trusting that the system is fractal, you could indirectly extrapolate the frequency of the very small patch reefs, which surely exist in the system, but just can't be resolved by the seismic data. So you're making a prediction there of what's going on. And of course, this is an oil and gas target. So it could be very interesting for the sort of prediction from that side of things. But you'd have to believe that rudist bivalves, behave in this curious way. And of course, it's very difficult to experiment on them because they are long gone. So we could go and start to look at modern bivalves, for example. And this is work by Johan van der Koppel. He's a very smart guy who's based in the Netherlands. Johan's got a position at the NIOS down in the south of the Netherlands, and also a position in Groningen in the very north. So he must spend a lot of time on the train commuting between jobs, and that's where he probably has all his fantastic ideas. And he started to work on mussels, bivalves of the sort you'd enjoy with onions and white wine sauce maybe. And these are mussels, and they occupy the Dutch tidal flats. And then you look at them here with an aircraft image, and lo and behold, they have this beautiful reticular patterning, very similar to what we see in the reefs. And if you zoom in, so now we come down to the individual sort of mussels you see here, that patterning actually repeats through scale. So here down at tens of centimeters, you get this lovely reticular patterning as well. And we know that the mussels are doing this biotically because you can pile them up in a big heap and leave them for a few weeks, and if you haven't killed them, they will arrange themselves back out into this self-emergent patterning. And Johan van der Koppel was really the first person to understood what was going on here because he could model it. So this is not a new idea, all the way back in the 50s with Alan Turing, of course, of code-breaking fame. He had recognized that if you have feedback loops which are offset in their scale, so a positive feedback on a long scale and a negative feedback on a shorter scale, he called this an activator-inhibitor model, you could get very interesting patterns starting to emerge from such a system. And really the fundamental work on this was done in terrestrial landscapes, and this is in North Africa. These are aerial photographs, 250 meter scale here, where the vegetation forms these curious patterns, sometimes referred to as tiger stripes or spots, and sometimes in between. And it was understood what was going on here was really a classic activator-inhibitor type arrangement where you had a short scale facilitation, that is where the vegetation was, it promoted infiltration of the little rainfall which happened in the region into the soil because the root mass broke up the soil, and that was a activator. It promoted more vegetation growth. But then between the vegetative patches, you get a crust that forms which makes basically the soil impervious, and that serves as a longer range negative feedback. And the tension between those two feedbacks starts to deliver this patterning. And this idea was taken to the mussel beds and it was simulated, and it's not quite a Turing type mechanism, but it's very similar. It's a Kahn type mechanism that the mussels are following here. And what Johan van der Koppel taught us, that the short range facilitation here is that the mussels like to clump together so they don't get washed away by the strong tidal currents. But if they clump too close together, they inhibit each other's ability to feed, and the tension between those feedbacks gives the emergent patterning that we see. Very interesting. So then you start to look at other carbonate systems. So this is work by Mardy McNeil and Jodie Webster offshore the Great Barrier Reef. And they're not looking at the coral part of the reef. They're going into a little bit deeper water, down to about 30 to 50 meters water depth, and looking at Halimeda mounds. So this is a calcareous green algae. We have it here, of course. And it was known to build bioherms, so mounds, it's constructional. But using LiDAR and multi-beam and zooming in here, this is a LiDAR image, you can see that the Halimeda isn't just simple mounds, which was thought. You see this lovely reticular patterning there. So that's another example of a carbonate system, it seems, playing this trick. All right. So, okay, I'm sure Bob Ginsberg, he would still say, so what? Well, then we start to work in the subsurface. So I was involved in a project and we were looking at seismic data from the Upper Carboniferous and Lower Permian acquired here in the northern Barents Sea. And this is a carbonate depositional system of mostly Permian in age. And you can see in the seismic, which was like very high quality, beautiful data, these reticular patternings. And this was a cold water bryozoan dominated environment, and it gradually warmed up into a warmer water photozoan environment. And the reefs here are built by Paleoplysina. which is a sort of a large Permian age calcareous algae, sort of a mega halimeda, you might think of it. And when we were looking at this seismic data, this was work from Equinor, the Norwegian oil company, it was presumed that this was a karst type system, where there had been erosion and of the limestone, and then there had been a transgression, and then simply the reef builders were just veneering it. But as the wells and the cores were drilled into the system, there was no evidence that it had ever been subaerially exposed. There was no exposure surfaces or solution enhanced fractures and fissures. There was just no evidence it was karst. And I thought, well, maybe we're dealing with a Permian age self-organized system here. And I thought we could do a little bit of comparative sedimentology, because that's what the Miamians, they like to do that. So we took a modern example, which was Alacran Reef in the Gulf of Mexico. And this is a satellite image, lovely reticular system. And we started to do a statistical comparison between the Permian and the modern. So we mapped out all of the reefs in the modern here in Alacran, and we plot them on our familiar axes. And thank goodness, Mother Nature, she's once you can understand her, she speaks the same language, and we get the lovely power law here describing the size of the reefs, or almost so. There was a little parts of the trend which plot slightly off where it should, and if you place those reefs on the platform, you see they're associated with a tectonic grain. There seems to be some sort of fracturing of the platform, so it seems that the tectonics, they can sort of upset the biology to a degree. Then we went down into the Barents Sea, and we look at the seismic here. So we have well control coming down through the system, so we can start to map out the different reef areas and the inter-reef areas. And then we plot them on our familiar axes. So in green here, we have the Permian age system, and in blue, the modern system, log probability of encounter versus the size of the reefs. And they look the same, and indeed they're statistically inseparable. So you've got two systems separated by 300 million years, totally different reef architects, different water chemistry, but the patterning is statistically inseparable. And you've got to think, well, how can that be the case? And we did other tests as well, not just looking at the size and the frequency. This is a power spectrum to look at the spacing of the reefs, and the modern and the ancient, they still plot exactly on trend. So what on earth is going on? Well, I think if you look at the satellite imagery, you start to get an idea of what the mechanism could be. So this is looking into the platform interior of Alacran in the Gulf of Mexico, our modern example. And what you see is that the system is evolved from simple patch reefs, really, which are then starting to weld themselves together into ridges, and those ridges start to develop and mature into wider ridges. And it even seems the shallower you get, the more intense this emergent patterning starts to appear. And in the way the image is enhanced, the browny sort of colour here, that's the living corals, and the whiter tan area, this is the detritus that they're producing. And you notice that the living reef organism is always striving to be on the edge position of the topographic height. You have the detritus in the middle, but this ridge, it's the living edge, if you will, which is where the construction is going on. And we believe the reason that the reef architect is doing that is because on the edge of the topographic high is where the boundary condition between the organism and the surrounding water is thinned by turbulence. And so that allows the reef organism to feed more effectively, but also, and probably more importantly, to shed its metabolites out into the water column. And so by constantly striving for this edge position, you end up with a packing problem, whereby once this system becomes restricted, as you can see, increasingly so into the shallows, the way of forming this reticular patterning is how to get the maximum amount of the reef builder into the minimum amount of space. And it really doesn't matter if you're Paleozoic phyloid algae, or a Mesozoic rudis bivalve, or a modern coral, you have the same metabolic underpinnings, and therefore you pattern in exactly the same way when you're faced with restriction. But of course, this sort of behavior, while it might be clever, is a little bit dangerous, because you look here at the degree of reticulation with decreasing water depth, and you become a victim of your own success. So the system becomes so restricted that eventually it ends up smothering itself. And if the high stand is long enough, you'll end up with a flat top platform here, or with a very complex internal anatomy. And with that, we start to talk about how emergent behavior can be dangerous, but it can also be absolutely lethal. So part of the characteristics of a self-organized system is this idea of tipping points, where you can have relatively subtle environmental forcings lead to very sudden and dramatic changes in the ecosystem. And coral reefs, really behave in this way in exemplary but terrifying fashion. And I spend a lot of time out in the central Indian Ocean in the Chagos here, because I was involved trying to declare this as a marine protected area, and it has some of the most fantastic reefs I've ever seen. And we were there, up until 2015, and then you come back in 2017, and it's heartbreaking. It's completely dead, and this is primarily due to the warming temperature of the oceans. And indeed, we were there when one of these bleaching events was taking hold, and you can see the nut brown corals in their healthy state turning sort of psychedelic bright colors, and then bleaching, and then really it's the diseases that move into the system afterwards, which really kills off the system. And you have to ask yourself, once you've seen this process play out a number of times, like, do reefs really have a future? We've lost, nearly 50% of them in the last 4 decades, and it's only accelerating. And you start to look at the record, and it can tell you, how reefs do behave. And it seems that when you have mass extinctions on the planet, and I think we're arguably witnessing the 6th great mass extinction, that reefs tend to be more severely and adversely affected of all the marine systems, and certainly over the last 500 million years or so. They are fragile, but they do come back, but they come back slowly. It can take up millions to tens of millions of years for reef systems to re-establish back to their full vitality. And when they do come back, they do so really rather gradually, certainly by no means on human timescales, by the way. So it seems that complex ecosystems like reefs take a long time to build and to rebuild. And when they do reappear, they're composed of entirely new reef architects, which start to fill that reef building niche. But as I've shown, I think they all have the same metabolic way. And to bring this to the modern, this is work by Morgan Pratchett in the Great Barrier Reef, who's looked at coral cover here through time. And yes, the trend is really rather depressing, and quite soon the 2020 data will be released, and indeed it'll be around 5% coral cover on our most iconic system. And the reason for this decline has changed. I mean, in the early days, crown of thorns were implicated. By the 90s, cyclones had also come into the fray, but coral bleaching and the diseases which come afterwards are certainly very important. And the list of insults that we foist on the world reefs just increases through time as the level of coral cover goes down. And I said in the beginning I was an optimist, but this is really a rather pessimistic sort of data set to be looking at. I think in the work that I've done around the world, there's really one method which I see might have an impact here, and that's the declaration of really large-scale marine protected areas. And I believe there's really 6 key ingredients here. 5 of them are due to governance, and the 6th is really a technological question. So the 6 ingredients: you have to have a no-take area, and it has to be well enforced, like no fishing and mining and extraction and so. And you also have to recognize that by declaring marine protected areas, you don't get a lot of benefit in the near term, 10 years before you really see the benefits, but then they accrue very quickly. You want to isolate that protected area from humans by large expanses of open ocean, ideally, and it should be really large. So this, the Chagos Trust, who I was working with and I was a director of for a while, we worked to declare the Chagos Archipelago a marine protected area, and it was nearly 750,000 square kilometers. That's the sort of scale that you have to be thinking about. And the 6th ingredient, which is a technological problem, is you have to know what you've got and its baseline status in order to implement meaningful conservation initiatives. And that's really a mapping problem. And that was the driving force behind this work with the Living Oceans Foundation. And we spent 10 years and a huge quantity of money, I will assure you, buying imagery and operating the ship, and we managed to map 1/5 of the world's reefs. You know, we can't do the 4/5 that remain. We don't have the fiscal power, but it was a good start. But I've started to work now with a program with NASA, which I think might offer a way to getting those remaining 4/5 of the world's reefs mapped and fairly quickly. So with that, I want to talk a little bit now about two technologies. One is called FluidCam, which is a CubeSat or drone-based system using an interesting property of the water surface to image the seafloor, and NEMONet is a neural network which is taking on the classification burden and to automate it. And this is work which comes out of Dr. Vaith Chirayath's lab. He's at NASA Ames in Palo Alto, and I'm part of the science team, and there's a technical and a gaming team, as I'm going to describe to you. And at the moment, the technology is mounted on a drone, or sometimes a series of drones, but we have a launch date for later this year to test the FluidCam in orbit using CubeSats. And this all comes down to the curious property that the water surface, distorts the seafloor. If you have any sort of wave, this is just in a tank, you can see that you distort the seafloor, and as a remote sensor, this tends to be a problem, that the distortion sort of obfuscates what you can see on the seafloor, particularly as you work at cruder resolutions from satellites. But the clever folks at NASA, they started to realize that you can use this distortion and you can use it as a lens to magnify the seafloor in this technique called fluid lensing. So this is a computer simulation. Actually, these are synthetic waves. We call these caustics. And you can see in the test case here, as we slow the imagery down, this incremental magnification of the target on the bottom of the pool and demagnification. And you can start using this simulation, which took nearly 50 million CPU hours at NASA, to understand the optical effect of the magnification at different water depths. So that's the first step. Then, if you can take very high frame rate imagery, and typically a video system is used for this, you can just cut out the bits of the imagery which give the magnification. This is the result, and then you can end up with an image which has the same fidelity as the original target, but this is with no water on the top, and this is using the water as a lens. And the result from the drone is you can get really sub-centimeter resolution, and possibly something not too dissimilar from orbit as well. And it all takes a huge amount of computer power. So this is where the NEMONet comes in. This is a deep learning algorithm that NASA have developed to automate the classification process, and these are some early results from American Samoa. So this is the original imagery with the water distortion, and NASA put the logo in here. This is the fluid lens result now, so the water's been mathematically removed, and because of the photogrammetry of how the imagery is acquired, we also get the bathymetry. So before we'd have to use LiDAR or so, we get a very nice bathymetry from the technique. And then you can start to use the NEMONet here. This is a two-part classification into living and dead. And then now starting to work on actual, sort of classes like seagrass and live and sort of coral assemblages that we would typically push for when we're doing marine mapping. Now, the trouble if you work with neural networks, well, first of all, they can be very powerful, but they need a lot of training data. So the way that NASA have worked with this is they've developed this gaming app where the presented with an underwater image, and then they spend and then they start to and the better you get at this, you score points, and then you get different levels, and it turns out people like that very much, and a big sketcher on the iPad, but this is what they do. that they're familiar with if they were snorkeling or scuba diving. And they're not very good at interpreting orbital imagery, satellite imagery, because very few people have the privilege of looking down at the Earth at that scale. So this is where we come in with NASA using the maps that we've produced. So we have 65,000 square kilometers, 1/5 of the world's reefs mapped from high-resolution satellite imagery and aerial, hyperspectral aerial overflights. And we can use that as the training data for the orbital data set, and we can use NEMONet now to start to work up to get the full global coverage. And I think this is a nice example of an academic to philanthropic to federal partnership, where we start with a lab at the University of Miami with meager resources. And I can tell if you come and visit my lab, meager resources are really, you know, the theme of the day. And then we partner with a philanthropic organization, Living Oceans, who has, you know, this vessel, and we can take these ideas and start to scale them up. And then once we have that hurdle jumped, we can then partner with a federal organization who has the sort of pockets deep enough to start to launch orbital platforms, and we can work our way up in that way. And hopefully, all being well, within the next couple of years, we should have a global high-resolution reef map. And I think from a conservationist standpoint, this is going to do a lot to kickstart meaningful conservation initiatives in areas which haven't yet started them. As a carbonate geologist, this is going to be a great data set that I can start to explore my own questions on emergent behavior also. So with that, I'll say thank you very much. I've got 3 final messages, particularly for the younger members of the audience. And the first is be passionate about your planet. I mean, we really do live on a fantastic planet, and it is worth conserving. Be proactive and get involved in its conservation. And I think most of all, remain positive. And I will say that as a coral reef ecologist, the news is pretty depressing, but I firmly believe that the window for action hasn't yet closed. It's closing quickly, but through really large-scale connected marine protected areas, there might still be a chance that we can move the needle on this. All right then, thank you very much.